Welcome to Part 2, Teaching Machines. In this section, we'll explore how we train AI systems to learn and make decisions, diving into the concepts of machine learning, neural networks, and other key methodologies that enable machines to perform intelligent tasks. In this slide, we're going to explore the motivation behind teaching machines and the primary methods we use to accomplish this. Just as we educate humans to perform tasks and make decisions, we need to teach machines to become intelligent. This allows us to create AI systems that can assist or even surpass human capabilities in specific areas. We'll look at three key approaches to teaching machines: learning by example, learning by rules, and learning by understanding principles. Each of these methods contributes to how we develop AI that can recognize patterns, make decisions, and adapt to new situations. In this slide, we delve into the essence of machine learning, which is the primary method we use to teach machines to become intelligent. Just like teaching humans, the process involves learning from experience and improving over time. We start by defining machine learning as the process of teaching machines to learn and improve without being explicitly programmed for every task. A key concept here is pattern recognition. Machines, like humans, learn by identifying patterns in data. These patterns are then abstracted into mathematical formulas, allowing the machine to make predictions or decisions based on new, unseen data. This similarity between how humans and machines learn highlights the incredible potential of AI, as well as the importance of teaching machines effectively. I want you to think about that concept where machines understand patterns, convert that into a math formula, and make prediction or decisions based on new and unseen data is the crux of machines learning, or ML. Please reflect on this. So, machines learn by converting their knowledge into mathematical formulas. This is how they can make predictions or decisions based on new data. Let's take a look at a simple example. We have a chart showing the relationship between height and weight for females and males, on average. Now, here's a quick task for you. Can you estimate what the weight would be for a woman who is 163 centimeters tall? Think about it for a moment. This exercise is similar to what a machine does. It uses the data it's been given to create a formula that can make predictions like this. Now, let's compare using fixed rules versus AI when solving problems like estimating weight from height. With rules, you might use a simple formula like this one. Weight equals 23 times height in meters squared for females, or you could just store every possible combination of height and weight. It's straightforward, easy to understand, and it gives consistent results without needing any training data. But as you can see in the cons, it may not work well for everyone. It doesn't account for individual differences, so the results might be off for certain people. On the other hand, AI takes a different approach. You feed in the height and weight data, and it uses machine learning to find patterns and create a model. The pros here are that AI can handle more complex relationships and is generally more accurate across different populations. Plus, it improves as you feed it more data. However, the cons include needing a lot of data to train the model, and sometimes the way the model makes decisions isn't very transparent. There's also a risk that any biases in the training data might show up in the model's predictions. So, while rules are simple and reliable for straightforward tasks, AI offers flexibility and accuracy, especially in more complex scenarios, but with its own set of challenges. This section is crucial because understanding the types of machine learning will help us see how AI systems are trained to learn from data in various ways, whether it's supervised, unsupervised, or reinforcement learning. All right, so now we're diving into the three main types of machine learning which are crucial to how we teach machines to learn from data. First, we have supervised learning. This is where we use labeled data, meaning the input comes with the correct output, and the machine learns to make predictions based on this data. It's often used for tasks like classification and regression, where the goal is to predict outcomes or categorize data. Next is unsupervised learning. Here, the data doesn't come with labels, so the machine has to figure out the patterns and relationships on its own. This type of learning is commonly used for clustering, dimensionality reduction, and anomaly detection, where the machine organizes the data into groups or identifies outliers without being explicitly told what to look for. Finally, we have reinforcement learning. This is a bit different because it involves an agent that interacts with an environment. The agent learns by receiving feedback, rewards or penalties, and adjusts its actions accordingly. This type of learning is often used in scenarios like game playing or robotics, where the machine has to optimize its behavior over time based on the feedback it receives. Each of these methods has its own strengths and is used in different scenarios, depending on the type of problem we're trying to solve. You know what is interesting? While building few complex models, we may end up using all types of ML, for example. While building OpenAI ChatGPT or any large language model, we all these techniques to build a complex model. Amazing, isn't it? To help explain unsupervised learning, let's use a simple analogy. Imagine you're given these blocks and you're asked to organize them. The question is, how would you do it? You might notice the blocks can be organized in different ways, by color, by shape, or even by size. You're not given any instructions or labels, so it's up to you to find patterns and decide how to group them. This is very similar to what happens in unsupervised learning. The machine isn't given any labeled data. Instead, it has to figure out how to organize or cluster the data on its own based on the patterns it detects. The options shown here are just two possible ways the blocks could be grouped, highlighting that there isn't always one correct answer. Just like in unsupervised learning, where the machine might group data in different ways depending on what patterns it finds most relevant. This method might be underappreciated, but it's incredibly powerful for discovering hidden structures in data, especially when we don't know what we're looking for. Now that we've discussed the concept of unsupervised learning using our block analogy, it's time for you to try it out yourself. This is an interactive demo where you can see unsupervised learning in action. When you click on the link, you'll be taken to a demo in Claude, where you can regenerate shapes and group them to see how unsupervised learning might organize them. You'll be able to experiment with different patterns and see how the algorithm groups the shapes based on the characteristics it detects, just like the way we discussed earlier. Go ahead and give it a try. It's a hands-on way to understand how unsupervised learning works and how it can identify patterns without any labels or prior instructions. Once you've explored the demo, we'll come back and discuss what you observed. Unsupervised learning, as we've seen, is all about finding patterns in data without any labels. But where does this actually get used in the real world? Let's explore a few key applications. First, we have customer segmentation in the marketing and retail industry. Here, unsupervised learning is used to group customers based on their purchasing behavior, demographics, or browsing patterns. This helps businesses tailor their marketing strategies, create personalized experiences, and ultimately improve customer satisfaction. Next, there's topic modeling in industries like natural language processing, NLP, media, and content management. In this case, unsupervised learning helps to discover the main topics within large sets of text data. This is especially useful for organizing and summarizing information from documents, articles, or social media posts. Another important application is anomaly detection in fields like finance, cybersecurity, and manufacturing. Unsupervised learning is used to identify unusual patterns that might indicate fraud, security breaches, or faults in machinery. By catching these anomalies early, organizations can respond quickly to minimize risks and prevent damage. Lastly, we have image segmentation in healthcare, autonomous vehicles, and computer vision. Unsupervised learning helps segment different tissues or organs in medical images like MRIs. Or it can help an autonomous vehicle recognize and segment parts of its environment, such as roads, pedestrians, and obstacles. These examples show how powerful unsupervised learning can be in understanding and leveraging patterns across a wide range of industries. Now, let's shift our focus to supervised learning, which is quite different from the unsupervised approach we just discussed. In supervised learning, we're not leaving the machine to figure things out on its own. Instead, we act as a teacher guiding it. Take a look at these blocks. This time, you're given more information. Some of these blocks are labelled as square and others as circle. But what about this yellow block? How would you classify it? In supervised learning, we provide the machine with labelled data, like the blocks labelled square and circle. The machine then learns from this data, so when it encounters new data, like the yellow block, it can make a prediction or classification based on what it has learned. This method is powerful because it uses past knowledge to make informed decisions about new, unseen data, which is why it's widely used in many real-world applications. Here's another example to deepen our understanding of supervised learning. This time, the blocks have more specific labels like big square, big circle, and small circle. Now, take a look at the yellow block in the middle. Based on the labels provided, how would you classify it? Would it be a big circle, small circle, or something else entirely? Think about the labels and how you might use them to make a decision. This exercise is just like what a machine does in supervised learning. It uses the labeled data it's been trained on to make predictions about new, unlabeled data. It's time for you to test your understanding with an interactive demo. When you click the link, you'll be taken to a supervised learning demo in Claude. In this demo, you'll work with a set of training data where each shape is labeled as either Type A or Type B. Your task will be to classify new shapes based on what you've learned from the training data. As you go through the demo, pay attention to how the model makes decisions and how it applies the labels to new shapes. This will give you hands-on experience with the principles of supervised learning and help reinforce the concepts we've discussed. Once you've completed the demo, we'll regroup and discuss what you observed and any questions you might have. Supervised learning is a powerful tool, and it's used across a wide range of industries to solve complex problems. Let's look at a few key applications to see how it's being used in the real world. Before diving into those examples, I'd like to share some insights from my own career. Over the years, I've found that more than 70% of the models we've built are based on supervised learning. But why is supervised learning so popular? The main reason is that with supervised learning, we have a clear idea of what we want to predict. We're working with labeled data, meaning that each data point is tagged with the correct answer, the outcome we expect. This makes it easier to train models to recognize patterns and make accurate predictions. For instance, if we're predicting how long a member will stay in the hospital, we have historical data on previous hospital stays to train the model. Or, if we want to recommend actions that will increase member engagement, we can rely on past data showing what has worked before. Supervised learning's popularity also stems from its versatility. It can be applied to a wide range of tasks, classification, regression, and more, which makes it the go-to method for many practical applications. When the problem is well defined and we have plenty of labeled data, supervised learning is typically the most straightforward and effective approach. Now, let's look at some key applications. Image classification. This is widely used in industries like healthcare, autonomous vehicles, and social media. Supervised learning helps classify images into predefined categories. For example, in healthcare, it can identify diseases in medical images, such as detecting cancer in X-rays. In autonomous vehicles, it aids in recognizing road signs and obstacles, ensuring safer driving decisions. In social media, it's often used for content moderation and face recognition. Predictive maintenance. This is crucial in manufacturing, aviation, and energy sectors. By training on historical data of equipment performance and failures, supervised learning models can predict when machines are likely to fail. This allows companies to perform proactive maintenance, reducing downtime and extending the lifespan of their equipment. From my experience, predictive modeling has saved companies significant amounts of money by preventing unexpected breakdowns. Sentiment analysis. This is especially important in marketing, retail, and customer service. Supervised learning algorithms are trained on labeled text data to classify the sentiment of customer reviews, social media posts, or support tickets. This helps businesses understand customer satisfaction, track brand perception, and prioritize responses. In projects I've been involved with, sentiment analysis has been key to understanding customer feelings about a product or service in real time, allowing companies to respond quickly to any issues. Fraud detection. This is critical in finance, e-commerce, and insurance. Supervised learning models are trained on historical transaction data labeled as fraudulent or legitimate. These models can then identify potentially fraudulent activities in real time, helping to prevent financial losses and protect customers. During my time in the financial sector, I saw firsthand how effective these models can be in safeguarding both businesses and consumers from fraud. These examples highlight how supervised learning is applied across various industries to enhance efficiency, accuracy, and decision-making. Its popularity comes from its ability to deliver reliable and interpretable results when the outcome is known, making it an essential tool in the AI toolkit. From my own experience, I can attest to its versatility and impact in solving real-world problems. Before we move on to the quiz, let's take a moment to reflect on some key concepts we've covered. First, let's consider: do machines learn as humans do? Think about the similarities and differences between machine learning processes and human learning. Reflect on aspects like pattern recognition, trial and error, and the role of experience in both machine and human learning. How do the three approaches to machine learning, learning by example, rules, and principles, compare to how we, as humans, learn? Next, consider the question: if machines can memorize all available digital information, are they truly AI or smart? Think about it, will you? Here, we're looking at the difference between memorization and true understanding or intelligence. Reflect on how AI systems process data, recognize patterns, and make decisions compared to simple data storage. Think about how the ability to apply information to new situations factors into our concept of intelligence, both for machines and for us as humans. These reflection points are meant to help you deepen your understanding of AI and machine learning, and to think critically about how these technologies work compared to human cognition. Now that we've reflected on the material, it's time for a quick quiz to see how well you've grasped the key concepts we've covered so far. This quiz will cover the basics of machine learning, including supervised and unsupervised learning, and some real-world applications we've discussed. You might also see a few questions around deep learning, which we'll explore more in an optional class at the end of today's session. Don't worry, this is just a way to reinforce what you've learned and to help solidify your understanding. Take your time, and once you've completed the quiz, we'll review the answers together. We've now covered the basics of AI and machine learning, and it's time to dive into a crucial part of how AI really works: algorithms, math, and the way they intersect to power AI. In this section, we'll explore the foundational algorithms that underpin AI systems, delve into the mathematical principles behind them, and discuss why understanding these concepts is essential for anyone working with or studying AI. Whether you're a math enthusiast or someone who's not so fond of numbers, don't worry. We'll break it down in a way that's accessible and relevant to the big picture of AI. And here's something to think about the next time someone asks, why do we need math in real life? Every AI system you interact with, from chatbots to recommendation engines, is built on the foundations of math. That's right. Those algorithms making decisions, predicting outcomes, and driving technology are all rooted in mathematical principles. How do you like them apples? Let's revisit this height and weight table to set the stage for our next topic. Looking at this table, can we estimate the weight for a female who is 180 cm tall? The data we have only goes up to 180 cm, so we'd have to use some kind of method or formula to make that estimate. This is where algorithms and math come into play. In AI, we use algorithms to process data and make predictions or estimations when we don't have direct data available. The ability to take known information, apply mathematical principles, and come up with a reasonable prediction is at the core of how AI operates. As we move forward, we'll explore how these concepts of algorithms and math underpin the decision-making processes in AI, allowing it to make intelligent predictions, just like estimating this weight. Now that we've set the stage, let's introduce a new concept: algorithms, often shortened to algo. An algorithm is a clear, step-by-step set of instructions designed to solve a problem or complete a task. Think of it as a recipe. Just like you follow steps to bake a cake, an algorithm follows steps to reach a specific result. There are a few key points to keep in mind. Precise. Each step in an algorithm is clear and exact, leaving no room for ambiguity. Definite end. Just like a recipe, an algorithm finishes after a certain number of steps, delivering a result. Input, output. An algorithm takes input, like ingredients in a recipe, and transforms it into an output, like a baked cake. Understanding algorithms is essential because they are the backbone of how AI processes data and makes decisions. As we continue, we'll dive deeper into how these algorithms work and why they are so critical in AI. Building on our understanding of algorithms, let's look at how they function in the context of AI. Algorithms are essentially the brains behind AI. They help machines learn from data and make decisions. For example, learning patterns. There are algorithms that help AI predict what you might like, such as Netflix recommendations, by analyzing your viewing history and preferences. Finding solutions. Other algorithms help AI solve problems, like finding the best route on a map, which involves a bit of math to calculate the quickest or shortest path. In summary, algorithms are what guide machines to think and act intelligently. They take the data, process it, and make decisions based on the instructions they've been given, just like following a recipe. As we dive deeper into how AI works, it's important to understand that math is at the heart of it all. Let's use this simple example to illustrate the point. Imagine we want to estimate the weight for a female who is 6.2 feet tall. The AI model is trained to understand the relationship between height and weight, which are our two variables here. The technique used in this example is called supervised learning. We've given the model data to learn from, where both the height and the corresponding weight are known. But what's happening under the hood? The AI uses a linear regression model, which is essentially a line that fits the data points as closely as possible. And the math behind this? It's something you might remember from middle school, a simple formula that calculates the best fit line. By using this linear regression, the AI can then estimate the weight for any given height, even if it hasn't seen that exact height before. This is a clear demonstration of how AI leverages basic mathematical principles to make intelligent predictions and decisions. Now that we've seen how AI uses math to make predictions, let's take it a step further with an interactive demo. In this demo, you can input different heights and see how the AI model predicts the corresponding weight. The model is using a regression equation, which you can see displayed on the screen. This equation was derived from the data, and it allows the model to estimate weights for heights that you input. Feel free to experiment by entering different heights and observing how the predicted weight changes. This will give you a hands-on understanding of how the model works and how small changes in the input can lead to different predictions. Once you've had a chance to explore, we'll come back together and discuss what you observed and any questions you might have. As we wrap up parts 1 and 2 of our course, let's take a moment to reflect on the impact and evolution of AI, transforming our world. AI is fundamentally changing how we work, communicate, and solve everyday problems. It's not just a futuristic concept. AI is very much a part of our present reality. Rapid progress. AI's development may have seemed gradual at first, but recent years have brought about significant advancements. We're seeing AI capabilities grow at an unprecedented rate. Mimicking human intelligence. AI enables machines to perform tasks that typically require human cognitive abilities, from recognizing speech to making decisions based on complex data. Everyday influence. Whether we notice it or not, AI touches our daily lives in numerous ways. Recommendations on streaming services, smart assistants, and even the way we interact with our devices. Inspired by the human brain. The complexity of the human brain has inspired AI researchers to replicate its functioning in machines, striving to create systems that can think and learn like we do. Learning like humans. We've taught machines to learn in ways similar to how humans learn, through experience, data, and trial and error. Mathematical foundation. At the core of AI is mathematics, driving the algorithms and models that enable machines to make sense of data and make informed decisions. Not yet human-like. While AI has come a long way, it's important to remember that it's not yet on par with human intelligence. But with ongoing research and development, it's improving every day. These points underscore the transformative power of AI, the progress we've made, and the exciting future ahead as we continue to push the boundaries of what AI can do.